Okay, so this is this is chapter 5. Okay, so it's about how we actually control microorganisms. So the history part of it is very interesting. So I added Semmelweis in here because he's the first person that really kind of figured out that disease can be spread from person to person and like how it's spread. And he came up with I kind of came up with the idea of aseptic technique. So this was in the 1800s, right? He died in 1847. So he was working in a hospital, and I think he was in France. And the idea was that up until this time, women usually gave birth at home with a midwife. But at a certain period of time, it became more trendy for them to go to the hospital to give birth. And women that went to the hospital to give birth were more likely to die from what they call puerperal fever or like childbirth fever than, so they got an infection, than women that gave birth at home. Okay, so what's the difference? What's going on? So he's seeing all these women die in the hospital, and he's like trying to figure out what could be causing it. Okay, and if you guys think about how the placenta pulls away from the uterus, right, and it leaves an open wound, and it's perfect for infection, right? So Semmelweis started noticing that the midwives that delivered babies in the hospital had better outcomes for the moms than the doctors. So he started watching the midwives and comparing them to the doctors. So he noticed that the midwives were way more into hand washing and things were clean compared to the doctors. So the doctors would move from patient to patient or even from the morgue where they were doing autopsies and to deliver babies without any hand washing or changing their apron or anything like that. So the moms were getting disease, were getting infections, probably from the doctors, right? So the doctors were transmitting bacteria from another patient or a dead body to the moms. So he proposed this idea and suggested hand washing, that kind of thing. And the other doctors totally criticized him, right? They told him he was crazy. They know what they're doing, that kind of thing. And he ended up in a mental institution and he died from an infection from a wound, which is sad, right? So Lister kind of picks up on what Semmelweis does, and he is at a later time, right? So he's further in the time period, like the idea has been thrown out there. Somebody already said it. So Lister came in and like said it again, but it was the right time. And people were more accepting of the idea, right? So he actually started by applying carbolic acid, which is phenol, which is a carcinogen. But it kills bacteria too. He put it directly on damaged tissue, and that would prevent infection. So they also aerosolized it and put it into the room where they were doing the surgery. So the physicians, they would probably end up with cancer. But Lister is considered the father of aseptic technique. So he's given credit for it. They named Listerine after him, right? Okay. When we are going to control microorganisms, right, we are looking at kind of two levels commonly. So we're looking at sterilization or disinfection. Okay, so sterilization means we are totally removing all of the microorganisms, even endospores, but we can't guarantee that we're going to get rid of prions. So prions are those infectious proteins that we've talked about. Okay, so totally getting rid of everything. Okay, disinfection is removing most of the microbes that might cause harm. So some are still present. Okay, so disinfectants are sometimes called germicides, right? And they're called bactericides, fungicides, virucides. Okay, so the side part, right? So side, like homicide, right? We're killing things, we're getting rid of them. Okay, disinfectants are can be used on inanimate objects. So not living tissue. Okay, and antiseptics are kind of the same basic thing, but you can use them on tissue. So you can use them on your skin. Okay, so a bunch of vocabulary. Okay, now this book has some other terms in here that I don't know that they're used all the time, but decontamination is just that they're removing pathogens to a certain level that's considered safe, right? So it's low enough that it's not going to cause infection in somebody. Sanitation reduces microbial population to minimize spread of disease. Okay, this is not a very good definition because it doesn't even tell you what level of control you're using. It just is like, okay, we're going to sanitize. Okay, preservation is that we're trying to delay spoilage, so something with like food. And then pasteurization is a brief heat treatment applied to food. Okay, so it reduces the pathogens, but it doesn't change the characteristics of the food. So we heat it up really fast, short period of time, gets rid of the things that are going to make somebody sick, doesn't change the milk or the juice or the cider or whatever that is being pasteurized. Whenever we're trying to control organisms, the situation that you're in has to be considered. Okay, so you have to go in, you have to say, okay, where am I and how sterile does this really need to be? Okay, so this picture is just supposed to show, okay, there's different levels. So there's like, if you're making food, okay, what do you have to do to keep people safe? If you are doing wastewater treatment, what do you have to do? If you're doing surgery, if you're making a drug that's going to be injected into someone, how sterile do you need to be? So this one, like really, really sterile, right? Okay, so we're gonna like look at we can look at control as to, okay, what do you have to do in your everyday life to keep yourself safe? And then you have to look at healthcare facilities and hospitals. Okay, what do we have to do to control pathogens from spreading in a healthcare facility? So we're always trying to protect the patient, right? We're trying to protect the worker too. We don't want them to be sick. So infections that occur in a healthcare facility are called healthcare associated infections, so HAIs, or they're called nosocomial infections. Okay, so that's an infection that you get if you're in a healthcare setting. You don't go in with it, you pick it up when you're in there. Okay, so why do we care? Why is this a big deal? So the first thing is, okay, so the patients are more susceptible because they're sick, right? Something's wrong with them or they wouldn't be there. Okay, and there are probably more pathogens there because that's where the sick people come. Okay, so this is like stepping it up. Okay, so the health care facility has to protect the personnel. So in the 1980s and the 1990s, so when HIV and AIDS became prevalent, okay, they started implementing universal precautions. And now there's universal precautions, but there's all these other kind of levels of it. So universal precautions are how we protect ourselves against blood and body fluids. Okay, now standard precautions take into consideration that other things can transmit disease besides blood. And then transmission-based precautions are disease-specific. So you can think about it, okay, so if it's something where you have to touch somebody to get it, or is it something that's respiratory? Okay, so these are really disease-specific. So how are we going to keep it from spreading? Okay, so how do we control? So hospital and other healthcare facilities. So in operating rooms, right, the instruments have to be sterilized. Prions are infectious proteins. They are really, really hard to get rid of. They just don't respond to disinfectants well at all. So prions are a new concern. I mean, they've been around for a while, but we haven't known about them like we've known about bacteria. So this picture is from your book, and they're just showing the red spots are like hot spots where there could be bacteria hanging out that you don't want it in there. Okay, now in micro labs, we have to eliminate the contamination in the samples, and we don't want to let it out into the environment. I don't know if this is worded right, but we don't want to let it out, okay? And we don't want anybody that's working in the lab to get it. So the CDC has designated 4 biosafety levels. So BSL-1 is biosafety level 1, so the microbes don't cause disease in healthy people. Okay, BSL-2 are moderate risk microbes, so they could cause disease, but there's a way to treat them. You would have to, it would be hard to get it. Okay, so they have limited potential for transmission. Like you'd have to take a bath in it or drink it or something to get sick. Okay, then BSL-3 are respiratory pathogens that could be potentially fatal, and there's a way to treat them. And then BSL-4 are easily transmitted deadly pathogens that we don't usually have a way to treat. So BSL-4 is the worst. You can Google it and you can look and see where the BSL-4 labs are in the country, and Maryland has a lot of them because of Fort Detrick and like NIH. Okay, now as far as food and food production, so if you think about it like in eating your food, so food lasts longer if you take out the microbes. So they either heat it, they can irradiate it or pressurize it, all right? And that doesn't change the structure of the food. Sometimes they add chemical additives, so preservatives, but those are regulated by the FDA so that you're not getting too much of it. There's always something going on with food production. And you can look at the FDA website and look at like voluntary recalls or recalls and see like what's happening. One of the big things lately was like the baby formula issue, right? And that was the plant that produces most of the baby formula in our country, which is sad that we only have one, like we have it in one place, had a problem with bacterial contamination. Okay, wastewater treatment facilities. So the goal of them is to ensure that drinking water doesn't have any pathogens in it. Chlorine has traditionally been used to disinfect water. They can form disinfection byproducts that can cause long-term health issues. Some organisms are resistant to the chemicals that they put in. So the wastewater treatment plants are going to be regulated as to what pathogens are in the water, but they're also regulated as to how they're getting rid of the pathogens in the water. And then there's a whole bunch of other things, right? So drugs, cosmetics, all that stuff. You don't want any contamination in them. Okay, now, how do you select an antimicrobial procedure? Okay, so there's lots of different ways that they do this, and there isn't a perfect method. So what you use depends on a bunch of different things. So how many microbes you have and what type they are, what is the situation that they're in, are they really bad, or how bad, what's the likelihood that they're going to cause infection, and like, what are you treating? Are you treating a piece of paper? Are you treating a liquid? Is it food? So like, there's lots of variables in this. It's not a one size fits all. Okay, so the categorized microbes in there, I have 5 ways of these 5 types of highly resistant microbes. So these are things that are hard to kill, and they fall into 5 categories. So the first thing is bacterial endospores. So they are the most resistant. They are hard to kill. They are survival structures for the bacteria. So the whole point of them is that they're going to stay around. Okay, so extreme heat or chemical treatment can get rid of them. Okay, protozoan cysts and the oocysts in them. So they're very resistant to disinfectants. If you get them, they are excreted in your feces. They can cause diarrhea. Okay, but if you boil your water or before you drink it, you can't get rid of them. Okay, Mycobacterium is like tuberculosis and leprosy. Okay, these have very waxy cell walls. So the cell walls are hydrophobic, so they're very resistant to chemicals and disinfectants. Okay, Pseudomonas species are very resistant, and they can actually grow in disinfectants. Pseudomonas is bad. And then there are non-enveloped viruses. So non-enveloped viruses don't have a lipid membrane around them, and they are harder to kill. So if you guys remember, think back to when the pandemic started and people were like, oh, it's good, you can use hand sanitizer. So SARS-CoV, which it has an envelope. Okay, so it's easy. Viruses with envelopes are easier to kill. So hand sanitizer works. Washing your hands works really well. Okay, so the number of microbes you have kind of determines what you have to do to kill it. So only a fraction of a population of microbes is going to die during a given time interval. So it's going to take longer to destroy a lot of microbes than a small one. Removing some organisms by washing something, like you wash it and then you disinfect it, that's going to reduce how long it's going to take. So like you pick up the waste and then you disinfect under where the waste was. Okay, so biofilms are hard to disinfect because they're layers. Okay, so there is this thing that they call the decimal reduction time. And the decimal reduction time is just the amount of time it takes to reduce like 90% of a population of bacteria. So this picture is just showing like you're going to reduce them like by tenfold every 5 minutes. Okay, now environmental conditions are going to influence what's happening. So dirt, grease, body fluids, they're going to interfere with the action of the chemicals if the heat can get in. Temperature and pH can influence it. Household bleach can kill the tuberculosis at a higher, way faster at 55 degrees than at 50 degrees, and it's more effective at a low pH, right? So there's just all these variables that they have to take into consideration when they develop a protocol for how to disinfect something. Okay, now, medical instrument categories. So our book classifies them in 3 ways. So the first one is critical items. So critical items are going into body tissue. Okay, so they have to be sterile. Okay, so they're going to include needles and scalpels. Okay, semi-critical instruments, they can go and they're going to touch the mucous membrane, but they don't penetrate the body tissue themselves. So they should still be sterile, right? So they should be free of microorganisms and viruses. They can have some endospores because usually the mucous membrane is going to protect them, but it's better if they're sterile, they're autoclaved, right? Some things can't be put in the autoclave though, so like an endoscope or endotracheal tube. The scopes, it's like something that's mechanical is going to be trickier, right? The last category are non-critical instruments and surfaces. So you're going to touch it with unbroken skin. So non-critical have a very low risk of transmission. So stuff like blood pressure cuffs, stethoscopes, the countertops, like the bed that you're sitting on. Okay, so physical methods. Okay, so there's going to be physical methods and there's going to be like chemical methods. So physical methods, the first one is heat. Okay, so heat is very reliable, very safe, fast, pretty cheap, non-toxic. You can use heat to disinfect and sterilize. It's been used for a very long time. Okay, filtration, irradiation, and high pressure treatment can be used on materials that can't be put into like an autoclave, that can't be heated to a high temperature. Okay, so we have 2 kinds of heat, right? Everything gets subdivided. So we have moist heat. So moist heat is going to denature the proteins that are in the microorganism. Okay, so boiling is a great moist heat, so it destroys most of the organisms and the viruses. Endospores survive. So you're taking it to 100 degrees Celsius for 5 minutes. Okay, pasteurization. There's all these variations on pasteurization now. So it's important. We use pasteurization to reduce pathogens and things that are going to spoil. So there's high temperature, short time. So milk, for example, they take to 72 degrees Celsius for 15 seconds. Ice cream, an example is they take it to 82 for 20 seconds. So there's just there's different protocols, but the main concept is high temperature, short time. Okay, ultra high temperature. So milk can be ultra pasteurized. You see that in the grocery store. So it can be taken to 140 degrees Celsius just for a couple seconds, and then it's cooled down really fast. So ultra pasteurization. Can milk be sterile? Yeah, sure it can. The milk in a box that has a shelf life, that is sterile milk. Okay, now autoclaving. So an autoclave is going to be pressurized steam. Okay, so we increase the pressure, and when we increase the pressure, that's going to raise the steam temperature, and that's going to kill the endospores. So what we're always looking for, we were looking for 121 degrees Celsius and at least 15 pounds per square inch. That's PSI. And it usually takes, depending on how much you have in there, 15 to 20 minutes. Okay, so this is a picture of what's going on inside an autoclave. So you're putting steam in. Okay, so the steam is coming in, right? And there's a jacket around it, and that's going to also increase the pressure. And we can show you. Oh, and I can find a video if you want to learn more about autoclaving. Um, if you're worried about prions, okay, you have to treat whatever you're going to autoclave with 1 molar sodium hydroxide before you autoclave it, or put it in the autoclave in the base. Okay, so just autoclaving by itself does not get rid of prions. Okay, now the autoclave has to be validated. So you have to prove that the autoclave is heating up to the required temperature in all of the spots in it, right? So if you think about your oven at home and how it might get hotter in one area compared to another, that's not validated. That would not be good enough for an autoclave, right? So the autoclave needs to be, it has to be heating up to 121, and the pressure has to be 15 throughout the autoclave if you're going to put stuff throughout the autoclave. So people, I mean, some people have gotten sick because the autoclave hasn't been, like, it's had a cold spot or something. Okay, you use autoclave tape on something, and that it starts out all looking like masking tape, and then if it hits a certain temperature, it turns black, like black stripes on it, or it says autoclaved. There, you also test it with bacteria. So you have spores in a little tube with media, and you autoclave it. And if the autoclave works, then the bacteria won't grow in the tube afterwards. So if they grow afterwards, you know your autoclave's not doing what it's supposed to do. Okay, now dry heat. Dry heat is like incineration, so burning it. Okay, so when you heat your loop, that's incineration. So turns it to ashes. So the wire loops that we use, they will incinerate medical waste or contaminated animal carcasses to get rid of them. So kind of like cremation. Hot air ovens will work, okay, but it's dry heat. So dry heat takes longer. So it's going to take a higher temperature and a longer time to sterilize. Okay, filtration, it's used a lot if something is heat sensitive. So something is a fluid, it's heat sensitive. So maybe it has sugar in it, and you can't heat the sugar up because it'll caramelize, it'll burn. So what you do is you put it through a membrane filter. So here's a little flask. Here's the sterile filter. Okay, and you use a pump, and the bacteria, the small things, will stay on the filter, won't go through. And then this is sterile. The size for sterile filtration is a 0.2 micrometers. That is the magic number. Okay, air is filtered. Okay, so HEPA filters, so high efficiency particulate air filters, they can remove almost all microbes that are bigger than 0.3 micrometers from the air. Okay, so in the biological safety cabinet that's in the lab, that is sterile, pretty close to sterile. And then there are specialized hospital rooms. There are clean rooms that they use to prepare vaccines, things that are going to get injected into someone. Then, so the air is circulating at a higher rate through these HEPA filters. We can use electromagnetic radiation. Okay, so high energy. So visible light stuff isn't, the wavelength's too long. That's not going to protect you, but smaller than purple for in like X-rays, gamma rays. Okay, they're bactericidal. There's enough energy in these waves to kill the bacteria. Okay, irradiation. So that's kind of basically the same thing, right? Gamma rays and X-rays. So it destroys the DNA and damages the cytoplasm, the membranes, the cell membranes, and they can produce reactive oxygen species. So you may see fruits and vegetables that are irradiated. So they'll use a gamma ray, and they'll zap it, and it sterilizes things that you can't heat up. So like the Petri plates that we buy to make the media that you use, okay, those are irradiated. Okay, ultraviolet radiation will destroy microbes. So I wish I would have bought this thing at Walmart when during the pandemic people were selling handheld UV lights with like a little battery so you could zap your wherever you were gonna like sit or whatever. So it damages the DNA. So they use it to treat to get rid of the microbes that's in air, on water, on surfaces. It doesn't penetrate very deep. Okay, so it doesn't go through plastic. And UV light, it also damages our DNA, so it can cause skin cancer. It can cause you to go blind. All right, so has to be strong enough to kill the bacteria, but you don't want to be exposed to it. Okay, microwaves, if you heat them up, like use it to boil water, okay, you could use that to kill something, but you have to make sure that it's heated evenly because the microwave doesn't heat evenly. So if it's not like uniform in there, bacteria could survive. Okay, now chemicals. Okay, so there are germicidal chemicals that are going to disinfect and sometimes sterilize. Okay, and the way that they're going to work is they're going to react with proteins, DNA, membranes, envelopes. Okay, lots of times they don't know exactly how they work, but they know that they work. Okay, chemicals are less reliable than heat, but they use them if you can't like heat something up. So if you have something big or you can't heat it, you can use chemicals on it. Some of them you can use as antiseptics. Okay, now the things that you have to look at when you're trying to decide what chemical you're going to use is you have to look at toxicity. Okay, so the benefits have to outweigh the risk. You have to see if they're going to be active, if there's organic material, so if there's vomit or something, right? Or is it compatible with the material that's being treated? Okay, or is it going to break it down? Is there going to be toxic or corrosive residue left? That would be bad. How much does it cost and can you get it? Can you store it? How do you have to store it? Is it stable? Will it last a long time? Okay, so lots of times now they make things more concentrated because that's going to decrease the storage space that's required and like what space is required to ship it. So like bleach used to be 5.25% sodium hypochlorite. Can't remember what the chemical formula is, but it's this. This is the active ingredient in bleach. Used to be 5.25. I bought some today and it's 7.5. So way more concentrated. Okay, and then the other thing that you have to take into consideration is it going to hurt the environment? If you're using a lot of it, what do you have to do before you can get rid of it? Okay, do you have to neutralize it before you get rid of it? Things have labels now that say it's safer. So the EPA, Environmental Protection Agency, says, okay, this is better than something else on the shelf. Okay, now these categories of germicides. So sterilants destroy all microbes, okay, and they're also called sporicides. So high-level disinfectants are going to destroy viruses and vegetative cells. Okay, so they're going to be used on semi-critical instruments. Intermediate, you're going to see them on being used on non-critical instruments. And then low level are going to be used on like the furniture, the floor, and the walls. Okay, so we got sterilants, high level, intermediate, and then low. All right, now this this gets kind of boring, so bear with me here. Okay, alcohols. So when we're using alcohol, they used to say we wanted something to be 70%. 70% alcohol, and then the other 30% would probably be water. Now they're saying they're kind of made the range bigger, so 60 to 80%. Okay, it can be ethanol, ethyl alcohol, or it can be isopropyl, which is rubbing alcohol. Okay, it doesn't work against endospores or non-enveloped viruses well. Okay, but it's going to destroy vegetative bacteria and fungi. So as long as you're not a spore or non-enveloped, alcohol is good. Okay, the way that it works is it's going to denature the proteins and it damages the membranes. So the water helps because the proteins are more soluble in the water. Okay, it also will last longer, won't evaporate as fast if there's 30% water in it. Okay, it doesn't leave a residue, it's cheap, non-toxic, so it's used a lot. Okay, so it can evaporate quickly, it can damage rubber, some plastics. Okay, and then there are some things that are dissolved in alcohols, and those are called tinctures. Okay, now aldehydes. So aldehydes are things that end in an hide or an aldehyde. Okay, so glutaraldehyde, formaldehyde, these orthophthaldehydaldehydes, OPAs. Okay, so they're going to inactivate proteins and nucleic acids. Okay, 2% alkaline glutaraldehyde is common liquid sterilant. So they immerse medical instruments in there for 10 to 12 hours. Okay, it is toxic, so you have to rinse after you do that. Formaldehyde, it can be used as a gas or as a liquid. If in anatomy, the animals that you dissect are preserved in some type of like formaldehyde. Okay, biguanides. Okay, one that you've probably heard of is chlorhexidine. Okay, chlorhexidine is used as an antiseptic. It stays on the skin and the mucous membranes. It has low toxicity, destroys bacteria, fungi, some enveloped viruses. So it's common in some skin creams, prescription mouthwashes, to treat periodontal disease, and it's used to treat catheters. So that's chlorhexidine. Ethylene oxide is really bad. Okay, so it's a gas, and they put things in like a room or in a chamber and they gas it. Okay, so it destroys microbes, destroys endospores, viruses, it modifies the proteins and the nucleic acids. So it can be used to sterilize fabrics, equipment, implantable devices. So like the artificial hip stuff, they're gonna gas it. It's also used for things like petri dishes and pipettes, things that are like sealed that you have to open up, like a syringe. So what you're going to sterilize goes into this chamber that's kind of like an autoclave, but it puts the gas into it and then it has to be exhausted out. Okay, so it's explosive, it's toxic, it's potentially carcinogenic, right? So if you think about it, okay, it's really good at killing all the microbes, it can hurt you too. Okay, so you have to get rid of it from the chamber by forcing heated air through for 8 to 12 hours. So, yeah. Okay, halogens are another class. So bleach falls into there. Okay, so chlorine, it will actually destroy all microorganisms, endospores, and viruses. It will burn your skin and your mucous membranes, though. You can dilute what you get in this bottle 1 to 100. Okay, you don't have to use it straight from the bottle. It does break down pretty fast, so you don't want it sitting around for a long time, or it doesn't do what it's supposed to do. It might smell like it, but it's not effective. So very low levels are used to disinfect drinking water, but it doesn't get rid of cysts. So Giardia and Cryptosporidium are bad diarrheas. Okay, it can react with organic compounds in water, and that's going to make it not work as well, and it could produce carcinogens. Okay, iodine, that's a halogen. Okay, so it's going to, yeah, I should have put halogen on there. So iodine, so it's going to get rid of vegetative cells. It doesn't really work on endospores well. It's used in alcohol when it's also used as an iodophore. So things like betadine, that's iodine. Okay. The bad part about it, Pseudomonas can actually survive in it, but we put it on our skin, right? You can put betadine on your skin, but Pseudomonas could get in there and survive. Metal compounds, these are one of the original sterilants or disinfectants that they found. So the metal compounds combined with these the sulfurs of the proteins, figured out copper really early on, and they used it to treat diseases on grapes in France. So they'd spray a copper solution. If the grapes were dying from a fungus, they would spray them with copper. Okay, in order for it to work, the concentration has to be high, so you can't ingest it or anything like that. Silver is used in some creams and bandages to reduce the likelihood of getting an infection. When babies were born, they use an antibiotic now, but Neisseria gonorrhea, right, that causes gonorrhea. So long time ago, gonorrhea caused babies to go blind. So the mom would have it. This was before antibiotics. The baby would be born, they would get gonorrhea infection in their eyes, and they would go blind. So they started putting silver nitrate drops on their eyes and in their eyes when they're first born to prevent them from getting STD from the mom. Now we put antibiotic ointment on their eyes. Peroxides, so peroxygens, hydrogen peroxide is one that you guys have all probably used. They're not as toxic. Cells can break it down. Cells that have catalase can break it down, but it works pretty well. So it's not as toxic. Doesn't damage materials, residue. They don't necessarily, if you have a wound that you're trying to get to heal, they don't want you dumping peroxide on it because it does damage the tissue. Okay, phenol. Phenol was one of the earliest disinfectants. It smells bad. It irritates your skin. It can cause cancer. I don't want to have to necessarily be around phenol, but it does kill bacteria. Okay, it works. I know I have hexachlorophene and triclosan on there, and I'm not sure why I put those two things on there. I'll have to figure that out and get back to you. Okay, now detergents. So quaternary ammonia or quats, these are actually cationic detergents. Okay, so detergents are kind of like soap, right? So these are ones that are positively charged. So quats are good in food prep. Okay, so they're low toxic. They are not very toxic. They reduce the surface tension of liquids, so that's going to allow you to get dirt and stuff out. It's kind of like a detergent, right? They have hydrophilic and hydrophobic regions, so they're going to help they reduce the surface tension of the liquid, just kind of like soap does to water, right? But the positive surface of the quats will attract to the negative charges of the cells, and then it destroys the membrane. Okay, so quats are found in lots of personal care products. Pseudomonas can grow in it though. Let's see. Preservation of perishable products. So we're back to food again. So chemical preservatives, I already kind of mentioned this, but you have to be able to eat them, right? It's going to extend the shelf life. So lots of times they use a weak organic acid. So benzoic acid, propionic acid, sorbic acid. So if you look at like your bottle of Coke, it'll have, I think, benzoic acid in it. So what that's going to do is it's going to affect the membranes, and that'll control any fungi or bacteria that are going to grow. Nitrate and nitrite are found in processed meats, so like bacon, hot dogs, lunch meat. Okay, so what they're going to do is inhibit the endospores from germinating, and it'll kill the other cells. So it does work against food poisoning. So stops the growth of Clostridium botulinum, which is botulism. High concentrations of the nitrates and the nitrites will make meat look pink. Okay, they don't want you to have too many of those in your diet because they can be carcinogenic, because they'll get converted to these nitrosamines. Okay, so low temperature, we talked about this. We talked about reducing water by salting things. Okay, so that's kind of on here. Salt, sugar, drying. Sometimes we dry things, or we freeze dry things, so lyophilize it. Lyophilization is freeze drying. And then drying, it doesn't kill it, but it's going to slow it down. And I think that is the end.